So we have got Simon Aubury, who is the principal data engineer coming from Thoughtworks. He's going to share with us how he can predict the cat is now fascinating. I think he probably have a device or one of those brain and machine interface attached, but I assume that is not the case, because otherwise we all will get into trouble. So I'm really looking forward to hear some of these and how it will be translated into some of the work that he and his organization does. Take it away, Simon.
Cool. Thanks, Jason, and thanks for the introduction. So thanks very much for the opportunity to join you folk today. I understand as a group, this might be a combination of folks interested in data engineering, data science, advanced analytics, but I'm hoping some of you, or all of you at least, enjoy talking about cats. So today it's hopefully going to be a bit of an interesting conversation. Answering a question that I had on my mind is, can we build a machine learning model to predict the location of my cat? Now, I don't know where folks are, but where I am at the moment, it's actually 2 o'clock on a Wednesday afternoon. And essentially, I wanted to build a machine learning model to predict where my cat was going to be. And honestly, that was likely to be a question of where was my cat sleeping right at the moment. So this is a bit of a story. This is a story about using a Bluetooth tracker, a number of microcontrollers, a large amount of Python, to essentially predict where my cat Snowy was going to be napping in the next hour. So this is about a 30-minute conversation. Happy to answer questions, but it might just be easier to answer those at the end. So by way of introduction, my name's Simon Aubury. I'm a principal data engineer and I work at Thoughtworks, and I'm actually joining you today from Sydney. I work as a consultant. I get to build some amazing data-driven products. I work with various platforms and technologies, but essentially working on cool ways to use data. So my day job is using machine learning. I work with streaming platforms and modern data engineering practice to solve ambitious problems. But you didn't come here to hear about me. You actually came here to hear about my cat. This is Snowy. She's our 4-year-old, ironically named Bombay. She's a lovely cat. But I've often had a bit of a question in my mind of, she wanders around the house, but I'm curious, could I train a machine learning model to predict where Snowy was going to go throughout the day? So this is a bit of a story about using some inexpensive hardware and a cat somewhat ambivalent to our data privacy concerns. I wanted to capture a whole bunch of data, train a model, and to essentially work out and build a prediction model to understand where Snowy was going to go throughout her day. Now, this is a combination of using some very localized location-based tracking in and around a house, some temperature tracking, and essentially using an extensive history of locations and favorite sleeping spots to start building up a bit of a theory around how we could actually use lots and lots of data and a training algorithm to make future predictions about where the cat was likely to go. Now, before I get on to the nuts and bolts of this, I kind of just wanted to do a very, very quick baseline, just to make sure that we're all coming from this with essentially a common understanding. So we're just going to do a very, very quick machine learning 101 boot camp here, just so we've got a level of common understanding. So obviously, you've seen slides like this in the past. I'm not telling you anything particularly new here. There's a whole bunch of scenarios which machine learning is useful for. It could be things like predictions, recommendations, understanding images. But in short, there are just some tasks that are really, really good for training computers. It might be hard for us as humans, but with sufficient horsepower and sufficient historic data, it's relatively easy to start talking about, well, how can computers start inferring outcomes on our behalf? So that's sort of a high-level theory around the styles of machine learning. But we're going to be sort of deep diving into the one on the left here, prediction. So when you start talking about prediction, we're talking about generally, sorry, I'm just going to wave my arms around to make this light go back on. Sorry, I will be doing that every 10 minutes or so. So generally, we're talking about taking a whole bunch of data to form an answer. And the classic conversation here is typically, well, could you train a machine learning model to detect fraud? You've got some historic information and you want to determine are these payment transactions correct or are they a signal of fraud? If you had this style of problem, you could actually start thinking about, well, what would a human do here if you had to put a human in the loop here to determine fraud based on historic transactional information? Well, you could write a computer program to do this. You could start thinking about how to come up with a whole bunch of business code and express this sort of business logic with a whole bunch of written code. But over time, this gets a bit cumbersome. So instead of the rules, could we get a machine to determine these rules on our behalf? So you've probably seen these kind of things before. If you take sufficient historic information, maybe a whole bunch of historic transactions and a whole bunch of historic indicators of whether those transactions were fraudulent or not, you might have enough of a historic base of information to make forward predictions. So on the left here, we've got sort of past transactions. Transactions 1 was fraudulent, but transactions 2 and 3 were not fraudulent. If I've got this kind of information historically, can I build a machine learning model to determine, well, are these sort of payment transactions fraudulent or not? So we want to come up with a rules-based system that's going to work this out for us. And there's essentially a sort of a flow that you go through. You take information, you generate a model, you make inferences around that. And you can sort of start this sort of feedback loop and start thinking about, well, the thing that you've created is a model. It's a deployable artifact. And that model will hopefully give you a level of indication about, am I solving my business problem? And this path is basically train a model, generate an inference, and make an outcome. And it's probably worth stressing here that the outcome isn't necessarily a yes or a no. It's more like an answer with a level of confidence here. So if we're talking about this idea around, I've got historic transactions and I want to determine, are they likely to be fraudulent or not? It's much easier to talk about these as probabilities. Is there a probability that these transactions are fraudulent or not? So in this case of transaction 1, we knew it was fraudulent. When we're inferring was transaction 4 fraudulent or not, we might be able to just say, oh, well, it's 95% likely to be fraudulent or not. So that was a big sort of arc, but you might be thinking to yourself, what does this mean to me and where does the cat come in? So it's actually not much of a stretch to jump from this idea about modeling banking transactions to determine fraud. There's a bit of an analogy here for taking historic data and working out where cats are. So using this sort of same mental model before, can I take historic location information such as time of day, weather conditions, and an observation about where the cat is? So 9 o'clock, it's a cold day. I saw that the cat was in a study. Can I take that historic information, build a model, and start building some inferencing around where she's likely to go? If I build this model, can I make an inference at well, 8 o'clock on a cold day? She's likely to be in the study, but maybe with a 95% confidence. So we can use this same kind of logic that we used for a banking transaction system and start thinking about, well, can I predict where the cat's going to go? So that was Bootcamp 101 for machine learning, but we kind of want to start thinking about, well, what's our approach for approaching a typical machine learning model? And how do we sort of break down the task if our goal is we want to generate insights on the fly? So we can typically break this down into 7 areas. We want to define a problem, get some historic information, clean it, train a model, evaluate the model, tune the model, and then go through that iteration of, is the model good enough? And if it's not, keep training until we get to a point of confidence that it's good enough, and then actually use the model. And this is the framework that we're going to be using for describing how to make cat predictions today. So let's start at the beginning. Let's define our problem. What are we trying to do here? We're trying to predict where Snowy the cat is going to be. So what what's the typical data that's going to be needed for a model like this? Now, it turns out if you start Googling the terms, what features does a machine learning model require for cat predictions? It turns out that there's not many hits on Google. So this is a bit of a theory of mine, is that there's going to be things that are going to be affecting Snowy's choice of sleeping location. Things like temperature, both inside and outside, time of day, whether it's raining outside, even the day of the week might become like significant features for training up a model. And I don't know how important these are, but I figure that these are the features that need to go into a model to start predicting Snowy's location. Okay, so I said that the first task here was to collect a lot of data where historically Snowy has been, because I need that history to actually start predicting the future. And I know that historic information needs to cover things like environmental features, such as temperature and rainfall. And this wasn't particularly scientific, but I decided I needed to essentially collect a lot of data. And I set an arbitrary target of collecting 3 months worth of hourly information to start building up a level of confidence that my model was going to start predicting things correctly. So let's move on to how do you actually collect data and start training a model. So like many cool side projects, the identification of a problem was an excuse to go and start buying stuff on the internet. So my goal of obtaining and loading a whole bunch of historic location information really was an excuse to jump onto the internet and start buying some cool hardware. Now, like I said, the ideal thing would be to start thinking about, well, how do I actually capture this information historically? Now, I said cats aren't great at data entry, so I needed a way of automatically collecting her location. And the approach I went for was to essentially just use a very, very small and lightweight battery device. I actually used something called a Tile, which is a small battery-powered Bluetooth tracker. And by tracker, that's probably a bit of an overreach. All it does is it simply sits on her collar and constantly transmits a regular and unique Bluetooth low-energy signal. And then I use little sensors around the house to pick up this transmitter. I ended up using 8 stationary sensors to listen for that Bluetooth low energy tile signal. These receivers, ESP32 based devices, and they run something called ESP presence. The details aren't all that important. I guess the takeaway here is that the closer Snowy is to each of these stationary beacons, the stronger the signal is on the receiving end. And all we have to do is essentially work out across all of these beacons, which one is receiving the strongest signal. If the strongest signal is received in, say, the study, that's a good approximation that Snowy is located in the study. So that gives you a bit of an idea about how to catch very, very specific room level location for where the cat is. But I also wanted to start capturing environmental conditions. I've noticed that Snowy the cat avoids going outside when it's raining, and she tends to fall asleep in warm but not hot rooms in the house. So I figured that it was important to start collecting these sort of environmental conditions, because I had an idea that temperature and rainfall were going to become significant factors in determining where Snowy was likely to be. So to capture this information, I used a number of low-cost devices from Xiaomi, which are both temperature and humidity sensors, and they're scattered around the house and also give me a very, very granular idea of where it's humid, where it's hot. And I had 4 sensors in the house and 2 outside the house to capture a level of environmental conditions everywhere. And I wanted to make sure that I could get all of this data into one place. So I used a platform called Home Assistant, which runs on a local home server. This is essentially an open source Python program which allows you to track and communicate with a whole bunch of home automation devices. It's essentially just a nice way of interfacing between commodity hardware. The only thing I needed to change for this project was out of the box. Home Assistant uses a SQLite database, and because I actually wanted to capture a lot of information over a long period of time, I chose to replace SQLite with Postgres. which allowed me to capture a whole bunch of historic information for a much longer duration. So in short, Home Assistant is a really, really fantastic community for interfacing across low-level hardware devices, and it's quite a good bedrock for capturing a whole bunch of low-level details, such as where your cat happens to be at what time of day. So that gave you a bit of a glimpse around how to capture all the information. But capturing that information is only one part of the journey. Obviously, I want to start preparing and cleaning that data so I can smooth the way for building a model to predict Snowy's location. So I actually have this problem of, I've got this kind of quite noisy and verbose data. I want to start cleaning it up so I can train a machine learning model. So let's move on to how I can actually do that data transformation. So the data I captured was very, very verbose and quite noisy. This platform that I'm using, Home Assistant, stores sensor updates essentially in a Postgres database in a table called the states table. This is super fine-grained. I'm getting updates every few seconds from all of the sensors. In short, I was getting something in the order of 18,000 sensor updates a day. So close to 20,000 updates a day. And my goal was to take all of this data and summarize it down and pivot it out, so I could just get essentially a snapshot of what each hour of the day looked like. Essentially, I wanted to get the most prevalent location along with the average temperature and humidity for each of the locations around the house per hour. So I've got this task of being able to take this quite verbose and noisy data, which is long and narrow. I kind of want to squish it down, summarize it, and pivot it out. So my goal is to summarize that long data set into something that can be fed into a machine learning model. So I chose to essentially use an open source tool called DBT. DBT is sort of a nice opinionated way of running a whole bunch of SQL commands. So it sort of helped me on my way to actually use an open source framework that is quite popular around analysts and data engineering, to essentially take my noisy transactional data and start forming it in a way that was going to be suitable to feed into a machine learning model. The TLDR here is that DBT allows you to transform data pretty quickly, and it's just a nice, simple way of transforming noisy data, in my case, noisy data, into something that's going to be easy to load into a model. In short, there's a sort of a quick capture of some of the code there, but you can just think of it as a number of SQL statements to collapse down, average, and pivot out the data. One of the nice things about DBT is it also generates beautiful lineage graphs, and it also gives you a nice sort of mechanism to use incremental feeds of data if you want to do incremental updates to your machine learning model. So in short, DBT is a great way of doing some of these sort of low-level data engineering tasks. So what have we done so far? We've captured a bunch of historic data, we've trimmed it down, and we've cleaned up the data. Now we're on to that kind of cool bit of being able to both train the model, evaluate the model, and then tune and improve the model. And this is where some of the open source frameworks, and I especially wanted to call out scikit-learn, is a really, really great way to get sort of moving in this space. So I chose to use a scikit-learn random forest library here, just to essentially start thinking about what are the significant features that are going to drive cat location prediction. So you can see some of the samples of code here, but I think the takeaway I really wanted to share here is that the data is pretty straightforward going in. It's day of the week, hour of the day, indoor, outdoor temperatures, basic features like whether it's raining or not, and an observation around cat location. And it's very straightforward to take some of this historic data, load it up, and essentially build a random forest classifier against it. One of the things I really, really like about scikit-learn is that once you've evaluated, built a model, and you can actually start testing it and actually see with a level of visualization which are the most significant features. one of the things that I found quite interesting is, as I was iterating on building these models, being able to sort of peek into the model and see which were the most significant features determining Snowy's historic location. Hour of the day is by far and away the most significant feature in a prediction model. And that kind of intuitively makes sense. She tends to spend overnights in some rooms and during the day goes somewhere else. So it's kind of intuitive that hour of the day is such a significant feature. Outside temperature is also a very, very significant feature in determining Snowy's location, and that kind of intuitively makes sense. One of the things that probably surprised me is how insignificant the "is raining" flag is. It turns out that whether it's raining or not is a really, really low weighted feature in the model. And it could be explained that there's only certain hours of the day that she's outside, so it's only certain hours of the day that conditions around whether it's raining or not actually make sense. So it's just, I think one of the things I found quite interested in diving deep into this data was which features were quite significant and which ones were the most prominent in determining the location of the cat. Another cool thing that you can do with a decisions tree is actually start visualizing how that random forest actually looks. And I've just done a big quick screen grab, but I kind of just wanted to point out a couple of significant parts of the decision tree here. At the top of the decision tree is a really important one. It's the hour of the day one. And it's actually determined that hour of the day, and this is clock hours, 0 through 7, so from midnight to 7 a.m. It goes down the left-hand side of this decision tree. And this kind of makes sense because our household generally wakes up at about 7 o'clock, and it looks like Snowy's location is highly correlated to whether it's before or after 7 o'clock in the morning. Another interesting thing about being able to visualize this decision tree is how significant day of the week is. It turns out that day of the week, so Monday through Friday, sends you down one part of the decision tree, and the weekends, so day of the week integers 6 and 7, send you down a different part of the decision tree. And again, this is kind of intuitively makes sense, but it's really cool to be able to think that there was actually a machine that determined this from observations, and we're actually looking at something that's been auto-generated on my behalf. And it's kind of good to be able to just do that visualization as just sort of a bit of a sanity check that this stuff kind of makes sense. So we've kind of gone down this long arc of taking a bunch of data, cleaning the data, putting it into a model. But you might be thinking to yourself, well, that was kind of cool from an observational sense. What do you actually do with it all? And I kind of wanted to share with you the final result of this, which is how to actually take a generated model and make forward predictions around where Snowy the cat's likely to be. Now, I used a framework called Streamlit, which is an open source Python library, and it's a really, really straightforward way for taking something like a predefined model and creating and sharing a web application. Now, I'm not a web developer, but I can pretend to be one by using a whole bunch of Python libraries. And I've got to say, I loved using Streamlit because it was a great way of taking my pickle file, wrapping it in a number of slider controls, and then building an online web app to actually talk about various scenarios. So you can fire this up yourself. You can either use that QR code or go directly to that Heroku app link, and you'll be able to see, using those sliders, where Snowy is likely to be at the moment. So you can put in hour of the day, day of the week, and actually see a real-time prediction with a bit of a confidence score down the bottom of where Snowy is likely to be. So that gives you a bit of an idea about, once you've taken an application, how you can actually embed it. You can actually do this for your own pets and animals, but I thought this was a great way just to demonstrate how to actually apply machine learning models in the field. So that was a long path, and I appreciate you giving me your time today, but I kind of just wanted to land with a few sort of conclusions and a bit of a lessons learned and a bit of a glimpse into things that I'm hoping to do next. I think one of the things I've been doing in all of this is both building these models, testing these models, and trying to get these models better over time. And intuitively, I think I'm still missing some features that are going to be quite significant in predicting where snowy is going to be. Turns out that snowy sort of behaves differently from whether it is raining at the moment versus whether there's rain on the ground. And I haven't really got a good way of doing that feature identification at the moment. One of the things I'm using in my model at the moment is humidity as a proxy for raining. And again, I don't think that makes sense. It can be humid and not raining. It can be raining without a significant change in humidity. So I'm kind of thinking that I've got some sort of features missing from the model. Another thing that's sort of quite significant is whether I'm working from home on a particular day or my wife is working from home on a particular day. That significantly changes the cat's behavior, but that hasn't fallen into the model yet. And I've also got this sort of overwhelming question in my mind of, well, are cats predictable at all, or am I just walking against a random number machine sometimes? So those are some of the things that are on my mind at the moment. And some of these things are essentially being built and being tested at the moment as part of a continuous evaluation of the building the best and most accurate cat prediction model. But I sort of started today with a bit of a question. And my question was, can you actually use historic information to predict the location of a cat? And my answer is yes. I'm getting somewhere in the order of 85 to 90% accuracy when predicting the location of my cat. I hope to make that prediction even better and more accurate over time. But as part of my goal of, can I actually solve the real world challenges of cat prediction? I think I'm on the way there, and I hope that over time, the accuracy improves and I can actually get closer to being able to answer definitively, yes, you can predict where my cat is. And with that, I just wanted to say thank you for your time, thank you for your patience, and thank you for your attention. If you're interested in finding out a bit more about this, you can look at all of the code for this project at this GitHub address, or you can actually read about this project on that Medium link. But if you only want to take away one link, that GitHub link will take you through to all of the blogs, materials, some sample data, and you too can start building out machine learning models to predict your own pet's location. And with that, I'm going to ask if anyone's got any questions.
Thank you, Simon. That was amazing presentation and pick out so many useful things. And I think it was really good that for you to quickly walk through about what the whole process is about and some of the background information. I'll kick off with the question. If anyone have any question, please feel free to jump in. My very first question is, I think I missed that bit, but when you were streaming the data, were you storing those data in local machine or in the cloud? And should that be the cloud? I think the biggest challenge that I often see in the streaming data, streaming event data is making the fine balance of how much data, stream data, to be saved, to be stored, to be used, but because otherwise the cost would just jump up.
Yeah, so super good question. In short, everything was stored in a Postgres database that happened to be running in my house. But there was nothing sort of stopping me storing this in the cloud, even though I'm talking about 20,000 rows an hour. In storage costs, it's still pretty trivial. And for a while, this entire project was running on a Raspberry Pi, so it's not the world's most taxing application. But in short, yeah, a lot of this stuff was processed locally. But yeah, cloud costs are pretty approachable, and I'm pretty sure I could have done this on an AWS free tier.
Thanks.
That was actually going to be my question, Simon. Kind of like, would you have seen this as a lot more effort to hook it up to the cloud, or it's all kind of similar anyway? Because I assume with the devices, could you have skipped having a server at your place sending that data to the cloud, and can you connect them directly to the cloud easily or not?
Yeah, again, a super good question. I think because I very much started essentially with a local Raspberry Pi as the center of all of this. Once I started collecting data, I didn't want to disrupt it. There's nothing particularly special about that other than that was my default choice, and I didn't really see a need to change it. But in answer to your question, yeah, the software could reside anywhere, the hosting could reside anywhere. And the only sort of practical thing is obviously some of these devices are in the house, they're communicating over protocols like Bluetooth Low Energy or Zigbee, and you still need essentially a little local broker to take on those signals, even if your ultimate destination was the cloud.
The other thing that captured my mind is that I was thinking, could I hook it up to my garage and finish the last step or not? And what I mean by that is, so currently I have got my garage door connected to Google Assistant, so I can voice control that. I can control that with my mobile phone, but I want to be able to save those two last steps so that it will just do it automatically. So what I was thinking before is that I could install a camera that would capture the plate number of the radio number of my motor vehicle, and then it will just automatically open as I come back. But I think that is a security risk where if someone just put whatever that number is, then it would just open the door. So that what you were presenting is giving the idea, what if I capture two data, so i.e. the visual data of capturing the plate number, but also if I have got a tile like you did with the cat, and I install a sensor near the garage, so it can tell the proximity of the location, combining those two, theoretically that should be slightly bulletproof to open the garage door for me without me doing anything.
Oh, I think that the sky is the limit when you start talking about the ways that you could do things with home automation. So I'm not giving you security advice, but yeah, definitely you can combine things like location. There's heaps of plugins for machine learning and observation through a whole bunch of cameras in conjunction with Bluetooth location signals, identification, and some cool things that you can do with geolocation. So I'd say, yes, you can do all of that. And if you're particularly interested, one of the plugins for Home Assistant is something called FreeGate, and you can download little TensorFlow models if you actually want to train them on things like number plate recognition or family members in your household if you want to train a model and have a level of low-level identification and classification. There's some cool frameworks out there already.
Good stuff. Anyone else have got any other question that want to ask Simon? Well,
I'm just going to say thank you very much for hanging around today, and yeah, I hope this gives you a bit of a background or maybe inspiration for some interesting use cases and applied approaches for machine learning.